In this video, I'm going to go through a sample problem where we talk about how we could simulate the effects of gravity on the human body when the human body is in an environment where they essentially feel weightless. And this happens if somebody's in orbit inside of a space station or a satellite or a spaceship around a planet or a moon. They're essentially in circular free fall or elliptical free fall inside of that thing, and they feel weightless. Or if astronauts take a trip to Mars or some other farther or distant location in our solar system and beyond, they would be far away from the gravitational attraction of a planet or a moon most of the time, and so they would essentially be in a weightless environment. And the problem with that is when you're in a weightless environment or a seemingly weightless environment, this has negative physiological effects on the human body. And we know this because of astronauts staying in the space station for a long time. They get muscle atrophy, they've got eyesight disorders, it can lead to decreased red blood cell production and other things. The question is, what can we do to try to minimize these negative effects on the human body if astronauts are going to travel in space for a long time or be up in space in orbit, essentially in circular free fall for a long time? Well, one solution has been, if you're inside of a space station, let's say you've got a circular space station, the gray right here is the interior, you could essentially make that space station start to rotate. If the astronauts inside of there were rotating with this spaceship, they'd essentially have some tangential velocity. Even without any significant gravitational forces, the astronaut still is going to feel a force in this situation if this space station is rotating like this. Remember, the astronaut's body wants to move in a straight line at a constant speed unless there's a force or a net force that acts on them. So if the astronaut's body wants to go in this direction, they can't essentially go in that direction ultimately because the space station is in the way. And so they're going to kind of like, their feet are going to essentially run into the curved space station, kind of compress it. And so that's going to push back with a normal force. If they're involved in circular motion because the space station is rotating, there's going to be a normal force pushing on them towards the center right here, right? And the only significant force in the astronaut is going to be the normal force, and that will be equal to the sum of the forces pointed towards the center. We know that anything that moves in a circular path at a constant speed, the sum of all the forces must point towards the center of its circular path, and that, in this case, it's a normal force. And the faster this space station rotates, the more their feet essentially are going to kind of run into the floor, and the more the floor is going to push back. The faster the space station rotates, the larger the normal force will be. So this is a way to change or vary how big of a normal force this person feels. If they can adjust the speed, the rotational speed of this thing, so that the normal force is equal to the gravitational force that the person feels on the Earth, they're going to essentially feel like they're standing on the Earth in terms of the normal force pushing up on them. Because remember, when you're on the Earth, you're typically sitting, you're typically standing at rest, and so the normal force you feel is the same size as the gravitational attraction that the Earth has on you. So your sensation of weight, which comes from the normal forces you feel, is equal to the force of gravity. Let's say we had a circular space station which had a radius of 50 meters, and so the person's feet are essentially 50 meters from the center of the point of rotation. Let's find out how fast we need to make this person move, their tangential velocity, so the normal force they feel is the same size as that on the Earth, which is just equal to the mass of the person times the gravitational field strength of the Earth. Remember, that's just 10 newtons for each kilogram. And so we've got a circular motion problem here, so we're going to have to use our circular motion equation. We know that the sum of all the forces on an object in circular motion at a constant speed has to be pointed towards the center. That's equal to the mass of the thing moving in a circle multiplied by the square of its tangential velocity divided by its radius of curvature. Well, in this case, what is equal to the sum of the forces that's pointed towards the center of the circular path on the astronaut? Well, it's just the normal force. So we have the normal force is equal to the mass of the person times the velocity of the person squared, divided by the radius of curvature. Well, remember, the normal force, we want to be equal to the force of gravity on that person on the Earth, which is just equal to m times g. So let's substitute in place of the normal force, the mass of the person times the gravitational field strength of the Earth. So we get m times g equals mv squared over r. we've got the mass of the person on both sides. We can just divide by the mass of the person on each side of the equal sign and it cancels out. And so our new expression is just G, or the gravitational field strength of the Earth, is equal to the needed velocity of the person squared divided by the radius of curvature. Well, we know the Earth's gravitational field strength is approximately 10 newtons per kilogram, or more precisely 9.8 newtons for each kilogram. So we plug that in for G. In this particular space station, we're saying it has a radius of curvature of 50 meters. So we multiply each side by 50, and we get that the square of the needed tangential velocity for the person is equal to 50 meters times 9.8 newtons per kilogram. That turns out to be 490 meters squared over second squared when we multiply these two things together. Since we're solving for v, not v squared, we're going to square root each side. So we get that the needed tangential velocity is equal to the square root of 490 meters squared over second squared, which turns out to be just 22.1 meters per second. So if the space station can move at 22.1 meters per second, they're going to feel a normal force that's the same as the gravitational attraction they would feel if they were standing on the Earth's surface. And this would tend to minimize those negative physiological effects that a weightless environment has. We're essentially creating a force that makes them feel like they have weight, when in reality, there is no gravitational force attracting them towards something. We just have the wall pushing up on them. The only other thing we could figure out is, well, if they needed to travel at 22.1 meters per second, how much time should it take this whole spaceship to rotate all around once? Or what's its period of rotation? Since this astronaut is moving at a constant velocity in this circular path, we're just going to use our constant velocity equation, where velocity is equal to displacement divided by time, or change in position divided by time. If we have one full rotation, that means they're going to travel around the outside circumference exactly once. So they'll travel the circumference, which is 2 pi r, divided by time. The time for one rotation is just the period. We use a capital T to represent that. And so if they're moving at 22.1 meters per second, the circumference is 2 pi times 50 meters, and we're going to solve for how much time it should take this thing to rotate once. Solving then for the period t, we get that the circumference is 314.2 meters. We're going to divide that by the velocity, or the tangential velocity, of 22.1 meters per second. The meter units cancel, and 1 divided by inverse seconds is just seconds. So we get the answer is 14.2 seconds. If this spaceship can spin around once every 14.2 seconds, the astronauts or anybody inside will be moving at 22.1 meters per second, and they're going to feel a normal force the same size as the gravitational force they would feel on the Earth, essentially simulating Earth's gravity.